Dealing with exponential function. First, let's go with exponential growth model. We have a of t is equal with small a times 1 plus r in exponent t. This is the growth model. The growth model, a is initial value. It has to be greater than 0. And b is the factor b. 1 plus r is the factor b. It has to be greater than 1. And factor b is 1 plus r. So those are the conditions. If we have an exponential decay model, is similar with the exponential growth model, but the only difference is here is a minus sign, minus r. So if a of t is equal with small a initial value times the factor b, which is 1 minus r, in exponent t. But the conditions are a little bit different. A has to be greater than 0, but b is greater than 0 and smaller than 1. And the b factor is 1 minus r. So let's take one example and let's see how we can apply in exponential growth model and in exponential decay. But in this video, I am going to take just one example with exponential growth model. And in the other video, I'm going to make another video which is going to include an example with exponential decay model. But first, let's go here with the exponential growth model. Example 1. The population of a large city was 4.5 million in the year 2010 and grew at a rate of 1.3% for the next 4 years. And first says, what exponential function models the population of the city over that 4-year period? First of all, let's take the initial value. The initial value is this here is 4.5 million. So A is the initial value, which is 4.5 million. Let me write million with a big M here. So is 4.5 million. And the R is a rate. The rate is equal with 1.3%. 1.3%. But because we have to use the numerical value of the rate in the formula, we divide this 1.3% by 100% and we get the numerical value of the rate, which r is going to be equal with a 0.013. And now we are going to see the formula. What was the formula for the growth? The formula is AT equal with A times 1 plus R. So this, let me rewrite the formula. A is equal A of t is A of t. Let me, because I'm not very fast writer with this pen, is A times 1 plus R, 1 plus R, everything in exponent t. And now let me substitute the known values, whatever I have for A and R. And for A here, what I have is 4.5 million, is a 4.5, is 4.5. And now if I'm going a little bit further, here is 1 plus, instead of the R, I'm plugging this value 0.013, 0.013, and everything is in exponent t, is in exponent t. If I'm simplifying a little bit further, this is going to be 4.5, and everything is going to be in 1 plus 0.013 is 1.013 here, and everything is in exponent t. But because we are looking here in the A for 4 years, so t is equal with the 4 in the A, t is equal with the 4 because we are looking for 4 years. Okay, over 4 years of how much is going to grow this population if it's a 4.5. And let me write here, instead of the t, I am writing 4, so here is a t. Instead of t, I will write 4 because I want to find the exponential growth of the population for 4 years. In 4 years, what is going to change? How much is going to grow? So here I have 4.5, and now I am plugging here 1.03, 1.013 in fact, 0.13, and everything here goes in exponent 4. And now I'm not going to get exactly, but I want to find approximately how much is going to go, because I'm going to approximate. I know I have to approximate in decimals. Anyway, first of all, let me try this to calculate in a calculator. Let me put a calculator a little bit here inside. So what do I have here? Let me go here, everything, erase it. I have 1.013 inside the parentheses. I'm going 1.013, and I'm going in exponent 4. If it's in exponent 4, I'm going to get 1.05, but I have to multiply by 4.5 million. So time 4.5, which is going to be 4.738. But if I'm approximating in 2 decimals here, I'm going to approximate in a 4.74 million. So it's going to be around 4. Let me check again. 4.74. Okay, 4.74 million people about. So this is how much is going to, how many people are going to live in after 4 years. But now, if the population continues to grow at the same rate, what will the population be in 2040? We use the same formula. But now, let's see in which population was this 4.5 million. It was in 2010. And until 2040, there are 30 years. Because there are 30 years, I'm going this t, the time, to take instead of the t, I'm going to substitute by 30, because I'm checking this in 30 years how much of the population grew in this city. So 30 is 4.5, and let's assume this is grew with the same rate, and is 1.013. Here is 0.013, and in exponent 30. And now we are going this to find exactly what it is. So again, I am not going to find exactly, but we are going to find approximately how much of the population grew. And let me erase this, everything what I have here. I have 1.013 in exponent 30, and is going to be this value, and time 4.5, and now I'm going to get 6.629. But if I'm approximating, it's going to be 6.63 million. 6.63. 6.63 million. So let me write this here, million. So in 2040, the population is, if it grows with the same rate, in the city is going to be 6.63 million people.